Imagine standing on a long bridge in the middle of a scorching hot day. The sun is beating down, the metal railings feel almost too hot to touch. The road surface is radiating heat. Now here's a strange thought. If heat makes materials expand, and bridges are made of steel and concrete, why don't bridges buckle, twist, or collapse during extreme heat? A large steel bridge can expand by several centimeters on a hot day, and if engineers didn't plan for that movement, the structure would literally tear itself apart. So the real question isn't why bridges survive extreme heat. The real question is how they're designed to move. Let's break it down. First, we need to understand something called thermal expansion. Every material expands when it heats up. Steel, concrete, glass, aluminum, they all do it. When atoms heat up, they vibrate more. That vibration pushes atoms slightly farther apart, which causes the entire material to grow. The change is tiny per meter, but bridges are enormous. Take a steel bridge that's 1 kilometer long. On a hot day, that bridge can expand by several centimeters. That may not sound like much, but if both ends of the bridge were locked in place, that expansion would create enormous internal stress. The bridge would start pushing against itself. Cracks could form, steel members could bend, and in extreme cases, parts of the structure could buckle. So engineers design bridges expecting this movement from the start, and they solve it with something surprisingly simple: expansion joints. If you've ever driven across a bridge and felt a small bump or heard a clunk sound, you've already experienced one. Those gaps in the road surface are not construction mistakes, they're intentional. Expansion joints are small spaces built between sections of the bridge. These gaps allow the bridge to expand during hot weather and contract when temperatures drop. Think of it like leaving space between wooden floorboards in a house. Without that space, the boards would swell and warp when humidity changes. Bridges follow the same idea. When temperatures rise, the bridge slowly stretches into those gaps. When temperatures fall, it shrinks back. No stress buildup, no structural damage, just controlled movement. But expansion joints are only part of the story, because a bridge can't simply slide freely. It still needs to support massive weight from traffic, wind, and its own structure. So engineers add something else underneath the bridge deck: bridge bearings. Bearings sit between the bridge deck and the supporting columns or piers. Their job is to carry the weight of the bridge while still allowing small movements. Some bearings are made with layers of steel and rubber. Others use curved steel plates that allow the bridge to slowly slide back and forth as temperatures change. This way, the bridge can expand in summer, contract in winter, and still remain perfectly stable under thousands of tons of weight. It's like placing a heavy bookshelf on sliders. The weight stays supported, but the structure can still shift slightly when needed. Now here's something interesting. Extreme heat doesn't just expand bridges, it can also affect the materials themselves. Concrete, for example, can weaken slightly when temperatures become very high. Asphalt can soften. Steel can lose some strength if temperatures become extreme enough. But the key word here is extreme. Bridges are designed with huge safety margins. Engineers calculate the hottest temperatures the region could realistically experience, then design the structure to handle even more. So even during intense heat waves, bridges are still operating well within safe limits. But occasionally, when temperatures become unusually high, you might hear about something called a bridge buckle. This happens when expansion joints fail or become stuck, preventing the bridge from moving the way it was designed to. When the heat expands the bridge but the joints can't open, the pressure builds up until part of the structure suddenly lifts or bends. It looks dramatic, but it's usually repairable and rarely leads to collapse. And when engineers see it happen, it's a signal that the expansion system needs maintenance, because the entire design of a bridge depends on one key principle. Movement is not the enemy. Movement is expected. A perfectly rigid bridge would actually be dangerous. Wind, traffic, earthquakes, and temperature changes constantly push and pull on large structures. The secret to strong engineering is allowing controlled movement rather than trying to eliminate it. That's why bridges have expansion joints. That's why they sit on bearings. And that's why even during extreme heat, when the entire structure is slowly stretching in the sun, the bridge remains stable and safe. So the next time you drive across a bridge on a blazing hot day and feel that small bump between sections, you're not driving over a flaw. You're driving over one of the most important safety features in the entire structure, and it's quietly allowing the bridge to breathe. If you enjoy learning how everyday engineering works beneath the surface, make sure you like the video and subscribe to the channel, because once you start noticing the hidden design behind ordinary things, you realize the world around you is far more engineered than it first appears. Thanks for watching.